We have two sample problems here. The first one starts out with a 10 kilogram box with a volume of 0.2 meters cubed that's submerged into water. What is the resulting net force? So we have a container. It is filled with some water, and we have a box inside of it. And we have some forces acting on it. We have the force of gravity, which is mg as usual. And then using Archimedes Principle, the amount of water that is displaced will provide that buoyant force based on the amount of weight of that particular chunk of water. And the way we find that buoyant force is based on the density, G value, and the volume of water. Now, what we can do is take a look at these two forces, and we're looking for the resulting net force. So we don't really know if the object is at rest, sinking, or getting pushed towards a surface. So we're going to go ahead and figure that out. So we have FB minus FG equal to our net force. So for our buoyant force, we have rho, which is the density of water, which is a constant of 1,000 kilograms per meter cubed, times 9.8 times the volume of 0.2, and then minus our mg, which is 10 times 9.8. So all we really need to do is find the product of those two and then subtract, and then we get 1,960 newtons minus the 98 newtons of weight, and that gives us our final answer of 1,862 newtons as our final net force, and that is directed upwards because that was from our buoyant force. So it looks like the object is going to get accelerated up towards the surface because our FB is clearly much greater than our mg. So the first thing you want to do is definitely draw out your diagram, which is going to be pretty similar in most cases. In this one, we just have our buoyant force upwards and our FG straight down, and then we just subtracted them because they're in opposite directions to find our net force. So let's go ahead and take a look at our second case now. Let's go ahead and separate this one out. And we have an object that's 5 kilograms and has an initial acceleration of 4 meters per second squared after being submerged in water. What is its volume? So in this one, we have a similar case, except it's giving us some kind of acceleration. We know the forces are unbalanced, and we're working our way around to solve for the volume. So we have a case where we have the buoyant force being counteracted by mg, and that equals the net force. Now we know the net force from Newton's second law is mass times acceleration, so I'm going to go ahead and slide that in. We have a mass of 5 kilograms, and we know we have some kind of initial acceleration of 4 meters per second squared. So let's go ahead and take care of that early on. Now for our buoyant force, we have this formula just as we used before. We have the rho of water, 1,000, our constant 9.8, and some kind of unknown volume minus the mass, times 9.8, and this side 5 times 20, or is 5 times 4, is 20 newtons. So what we can do is we can go ahead and simplify the look of our problem a little bit. 1,000 times 9.8 is 980, with our coefficient as our coefficient in front of the v. And then we have 5 times 9.8, which is 49. Let's go ahead and add that 49 to both sides. And we're just about done with the problem now. All we have to do is cancel out the 980 by dividing on both sides, and then we have a final volume of 0.007 meters cubed. So in this case, we use the same ideas as the previous one, as in we have our two forces, our buoyant force up and our force of gravity down, using Archimedes Principle, except on this side, our net force, we had to break it up into our two components, mass and acceleration, and then we had an unknown v on this side. So just a little bit more algebra, but very similar ideas to solve for our second solution as well. So in orange here on the left, we have a sphere that's hung by a string and then lowered into a bucket of water until it is completely submerged. What is the radius of the sphere if the string has a tension of 35 newtons? So we have a string with a sphere attached to it. It is 5 kilograms and it is in a container that is filled with water. All right, so there's our initial drawing right there. And let's go ahead and label some of our forces so that we can start to set up an equation and then plug some variables in. So of course we have the force of gravity pulling straight down as usual. We have our force of tension from the string that's got to be pulling it up. And then in addition to that force of tension, we have a buoyant force applying a force upwards as well, which means that if the object is static, is at rest, then we have the buoyant force plus the force of tension pulling it upwards, and then we have the force of gravity counteracting that, so we're going to subtract it, and that would equal 0 newtons in total to keep it in static equilibrium. Now from there, we're going to break our formulas apart and put in some different values as well. So for the buoyant force, we're going to use the formula rho Vg. For the force of tension, we know that it's 35 newtons from the problem. And for the force of gravity, we know we're going to use mg. So from there, let's go ahead and plug in some values. We know the value of rho, the density of water, is always 1,000 kilograms per meter cubed. For the volume of the sphere, that's unknown. We have a constant g value of 9.8 plus 35 minus 5 times 9.8. So what we can do here is we can go ahead and combine these two, and we would get negative 14, which means that if we add 14 to each side, then we have 14 equal to, and then we'll take 9.8 times 1,000, and then we get 9,800 as our coefficient that is in front of the v. And then we can go ahead and divide both sides by 9,800, and then that's going to give us our volume of 0.0014. All right, so we're almost there. We know that our volume is 0.0014. So what we can do is we can take 0.0014 and then set that equal to the volume of a sphere. So we have 0.0014 equal to pi r cubed, the volume of sphere, and then we do a quick algebra step or two, divide each side by pi, and then we are going to cube root this final value, and then we get a final radius of 0.076 meters. So after you divide 0.0014 by pi, what you can do is, if you can find a cube root button, go ahead and use that. If not, you can raise it to the 1/3 power, and that would be the equivalent of taking the cube root. And then you would go ahead and find your radius from there. So to sum things up, what we want to do is, if we're working on a problem like this, we're going to have our force of gravity as usual, and then our buoyant force as usual if it's a buoyancy type of problem. And then we want to make sure we are aware of which way the force of tension is pulling. In this case, since it's attached to the top part of the sphere, that means the 5 kilogram mass is trying to sink, and the force of tension is restricting it from sinking. So it's going to help with that upward force. And then once we set everything equal to 0, because it's all in static equilibrium, we can break apart each of our formulas, plug in our numbers, and then do a little bit algebra to solve for our radius. Okay, so let's go ahead and clear this work away from our first problem and take a look at our second one. Now for our second problem, we have a 0.3 meter cubed 20 kilogram ball that's attached to a string from the bottom of a container filled with water. What is the force of tension in this string? So for this particular one, we have an object that is trying to float towards a surface, and we have tension that is pulling it downwards. So in this case, we have the ball that's submerged in water, and we have the force of tension pulling it downwards, and we also have the force of gravity pulling down as usual, and then counteracting both of those is the buoyant force, the weight of the water that's displaced by that sphere. So in this case, we can go ahead and set up our formula as FB minus the sum of our two downward forces, and that's equal to 0 newtons because the object is static. Now, what we can do is break everything up into our formulas. We have rho Vg minus mg minus ft equals 0. And what I can do is I can go ahead and add ft to both sides. So I can have ft over here because I'm looking for the force of tension anyway. So I want to go ahead and isolate that. And I have the rho of water, 1,000 kilograms per meter cubed. We have the volume displaced, 0.3 meters cubed times a constant 9.8. And then we can go ahead and subtract the mass of the ball, 20 kilograms multiplied by 9.8. So find the product of these three numbers. We have 2,940 newtons minus the weight of 196 newtons, and that will give us our final force of tension. All right, so for this one, it seemed slightly less complex, especially after doing the first one. We didn't have to use any additional formulas like the area of a sphere. All we had to do is draw in our forces, use Newton's second law, which is taking the sum of the forces and setting it equal to mass times acceleration. But there is no acceleration in this case, so we have a total of 0 newtons off to the right. And then break everything into our formulas, and we were able to just kind of plug in everything we needed, and then take the difference of those two values, the buoyant force and the force of gravity, and that gave us our force of tension of 2,744 newtons. We have a 350 gram hollow cylinder that's 15 centimeters tall that has 10 centimeters of it submerged in water. How much mercury is required to make the cylinder become completely submerged? We're looking for some kind of volume in milliliters. So we have a cylinder that is partially submerged in water. So we have a container, it's filled with water, and we have some of it that is submerged. Let's see, we have 10 centimeters of it submerged, and it has a total height of 15 centimeters, so an additional 5 centimeters up here. All right, so let's go ahead and start off with some forces. We have the force of gravity, which is basically the weight of the cylinder, and then we also have the buoyant force pushing upwards, which is equal to the weight of the water that's displaced. That is our initial scenario. And then as soon as we add some mercury in there, then we're going to have an additional force downwards from the mercury. And we have Hg, our symbol for mercury, and then I'll put CYL for the Fg of the cylinder. All right, so initially we have the buoyant force that's equivalent to the force of gravity of just the cylinder because it's in static equilibrium. Now, at this particular moment, we can say that we have rho Vg equal to mg. The g's are going to drop out. We have the rho of water, which is our constant, 1,000 kilograms per meter cubed, as shown up here. And we have a volume that we don't know as of now. And then that's equal to the mass of the cylinder. It says 350 grams. Let me go ahead and divide that by 1,000 and make it 0.35 kilograms. Now, I can't really go too much farther. So what I'll do is I'll do a little substitution and substitute in the area times the height for our volume. And then now we have 1,000 times the area, and then times our height. Our height that's submerged is 10 centimeters. So I'm going to go ahead and divide that by 100 and call that 0.1 meters, so that we're all in our standard units of kilograms and meters. Now from there, let's go ahead and set that up over here. 1,000 times 0.1 is 100. So 100 times A equals 0.35. Divide both sides by 100. And that gives us our area of 0.0035 meters squared. Now, we weren't looking for area for our answer, but that will probably be some useful information later down the line. So let's go ahead and add that up here into our list of known variables. And then clear some space and see if we can find a solution that will help us find the volume of mercury. Now for the second part of our problem, we are going to have this cylinder become completely submerged. So we still have a buoyant force down, but we're combining our two FGs, our FG for the mercury, and then our FG for the cylinder as well. So we're still going to have rho Vg equals mg of the mercury plus mg of the cylinder. And then our g's are going to drop out. And then we have the mass of the mercury, Hg, plus the mass of our cylinder, which we do know. We call that 0.35 kilograms earlier, and it still is. And then over here, we have rho of 1,000 still, times our volume. And we didn't have our volume previously, but we do know volume is area 0.0035 times the height. Now the height is now the full 15 centimeters, now that we're saying that this is the portion of the problem where it's becoming submerged. So 15 divided by 100 is 0.15 meters. So when we finish working this out, we get 0.525 equals the mass of mercury plus 0.35 kilograms, the mass of the cylinder. And then we're going to subtract this. And then we have a mass of mercury, which is 0.175 kilograms. All right, so that looks like a helpful piece of information, although that's not our final answer, because we're looking for a final answer that is a volume in milliliters. So we do know that if we take the density of an object, the density is the mass over the volume. Therefore, the mass is equal to the density times the volume. So that's exactly what we're going to use. We have a mass of the mercury. We know the density of the mercury, 13,600, as given by this setup in the very beginning. And then we can find the volume. So we're going to divide both sides by 13,600. And then we're going to get a very small value for our volume. 0.00013 meters cubed. All right, so we're almost there. It looks like we're getting pretty close. We do have the volume, but we want to do a little bit of converting. So let's clear a bit more space. Now what we can do is we can take our volume and we want to convert this 1 meter cubed into centimeters cubed. Okay, so we have 100 centimeters. And then once it gets cubed, it's basically 100 multiplied by itself 3 times. So which is actually going to give us 1,000,000. So let's go ahead and actually cross this out and we'll call it 1,000,000. Okay, so that's sort of tricky when you're doing some converting with units that are representing the volume, because everything gets cubed. The 1 cube doesn't really matter because 1 multiplied by itself 3 times is going to be 1 anyways, but 100 multiplied by itself 3 times is going to give us 6 zeros, which makes 1,000,000. So 0.00013 times 1,000,000 gives us 13 centimeters cubed. And 1 centimeter cubed is actually a milliliter. And that takes us to our final solution. We have 13 milliliters of mercury that need to be added into our hollow cylinder, and that's going to completely submerge it. So I hope all those steps were helpful in helping you learn about buoyant forces, how to use the force of gravity, and apply a bunch of different skills in order to find the volume of mercury. Thank you for watching and listening.